Hi everyone, I'm Kevin Malay, and today I'm going to present our work called DeepScale, online frame size adaptation for multi-object tracking on smart cameras and edge servers. So before anything, let me have the outline for our work. First of all, we're going to have an introduction of multi-object tracking. Then we come up with an observation and some motivations for multi-object tracking on edge devices. And then we continue with presenting our work about tracking with adaptive resolutions. And finally, we present some experimental results for DeepScale paper. So in terms of introduction, we can have a background like tracking on edge device. For this sort of architecture, we can observe a smart camera which is connected to edge server, and both of them can handle tracking model. For the tracking task, we have several variety of sections like object detection, object re-identification, and finally, we have object association to construct the trajectories. So, and here is the related works to our DeepScale paper, where we have identified three categories of recent works. And the first one is adaptive frame size in visual processing. In this case, there are some differences between DeepScale and this category. First, the metric to determine the optimal resolution is tailored to mode, in that it considers both target detection and re-identification across frames. Second, in DeepScale, feature extraction is shared between resolution prediction and object detection, and thus incurs small overhead. Lastly, DeepScale allows users to choose suitable accuracy, latency trade-offs, and at runtime without having to retrain network or store extra models or branch. The second type of works is are related to real-time multi-object tracking. In contrast to this category, which attempt to accelerate visual processing or mode, we adapt the sizes of input frames to achieve a good trade-off between inference time and tracking accuracy. And finally, the last category of works are related to efficient edge cloud architecture. Although these architectures split computation loads between end devices and edge servers, they are not designed for mode and fail to account for multi-object detection quality in optimizing the end-to-end performance. So now let's talk about some observations and motivations of our work. Based on an experiment that we conducted on a multi-object tracking task, we have identified three sections of tracking task, like object detection, object association, and other operations like I/O or image resizing. So here is the timing breakdown, and as we can see, even more than 50% of timing is spent on object detection. So it is relevant to say that any works to accelerate the performance of object tracking should be related to object detection. And also, as the first motivation, let me introduce this table where we have conducted some experiments on mode 17 dataset with Tesla P100 GPU. And we have used fair mode multi-object tracking. So as we can see, we have conducted our experiment for different resolution. As we expected, larger frame sizes generally tend to result in higher tracking accuracy at the cost of longer inference time. And as the second motivation, we have performed an experiment on some sort of clips with different resolutions. And this figure presents the detectability normalized by the detectability of the highest of the full resolution. And we can see that for those situations where objects are far away from the camera, and those scenarios that we have crowded scenes, there is a huge gap between the performance of high resolutions and versus low resolutions. And the interesting fact is that as we deal with those frames that are having close objects to the cameras without any crowds in a scene, the performance of there isn't that much noticeable difference between high resolution and low resolution. So in this scenario, we can say that there is no one size fits all frame size for real-time mode tasks. Therefore, an adaptive scheme based on the analysis of visual content in scenes is needed in order to find a good trade-off between tracking accuracy and speed. And now let's talk about our paper. Here's our method for tracking with adaptive resolutions. As a problem statement, here's the big picture of our work, where to take advantage of shorter inference time of smaller frame sizes, DeepScale aim to select suitable resolution on the fly without compromising tracking performance. And when it is developed on smart cameras, depending on their computation capabilities and access bandwidths, the DeepScale pipeline can flexibly partitioned between smart cameras and edge servers. And also here is the DeepScale pipeline, where this model is designed to be agnostic frame size selection approach that operates on top of existing fully convolutional neural networks, fully convolutional network-based trackers to accelerate tracking throughput. In the training stage, we incorporate detectability into one-shot tracker architecture so that DeepScale can learn representation estimation for different frame sizes in a self-supervised manner. To further reduce computation overheads, resolution estimation in DeepScale is shares common feature extraction layers as object detection model. So during inference, every K-frame it can adapt frame sizes according to the complexity of visual content based on the user control parameters. And based on that, it continues to process frames with that optimal resolution for the rest of K-1 frames. And here's more details of training time and inference time. So during training, using equation number 2, DeepScale learns the quality of detection for each resolution offline. We have formulated the detectability score using focal loss. And when it's combined with the detection, they construct the overall loss for our training stage. And for the inference time, we aim to find the optimal resolution. So given the, so here's the equation that we determine the optimal resolution based on equation 5. So given user accuracy latency requirement at runtime, it selects a set of suitable thresholds and adapts the input size by solving equation 5 online. So gamma R is the user specified threshold regarding resolution R. So, right. Here is the introduction. Also, in this slide, let me introduce you DeepScale++, where it trains our model over different resolution. Remember, DeepScale was designed to determine the optimal resolution, but in the regular DeepScale, we don't have any training over different resolutions. So in this case, we introduced DeepScale++ to introduce our network for different object over variety of resolutions. So in this case, it's more probable to perform better performance and accuracy. So here is our plan for computation partitioning between edge device and edge server. For smart cameras, depending on their computation capability and access bandwidth, DeepScale pipeline can be flexibly partitioned between smart cameras and edge servers. So, for example, we have first type of architecture where it's only on smart camera. So in this case, the whole task of the entire task of object tracking is performed only on solely on smart camera. As the other case, edge server only, we have the whole processings on this edge server, and it only and the smart camera only sends full HD resolution to the edge server to process tracking task. And as a third architecture, we call edge server only with adaptive frame size transmission, where again server is the main part of the computation. However, the communication between edge server and smart camera is based on the optimal resolution for each keyframe. So once the optimal resolution is determined, till then, smart camera sends the rescaled images each frame. And the final architecture is about edge server assisted tracking. So in this case, smart camera is a main part of the computation. And it only interacts with server to retrieve the optimal resolution and some and get some results from the server, like re-identification features and the detected bounding boxes. And once it's determined, a smart camera continues the tracking task for the rest of K-1 frame. And now here is the some details of our experiment. So we have conducted our experimental part, our experimental tasks in over 4 different data sets, modes 15, 16, 17, and 20. We have our DeepScale and DeepScale++ are inspired by Fairmont, which is based on PyTorch. And we conducted our experiment using Tesla P100 GPU, and we picked DLA34 architecture for server-side computations. Since DLA34 delivers great tracking accuracy and performance compared to other architectures. And in terms of our testbed details, we picked NVIDIA Jetson TX2 to simulate a smart camera, which is connected to GPU server through Wi-Fi communication. And we selected YOLO architecture due to its light weight on the edge devices. So here's the DeepScale ++ configurations. So based on the user-specified control parameters, we can design DeepScale ++ for different needs. For example, we can have configuration C1, where we only work with resolution 600, 500, and if neither of them are appropriate, we work with 700 resolution. So given this explanation, we can see the percentage of frames that are selected by DeepScale for C1. As we can see, around 60% of the frames are selected like 700, resolution 700, and around 31% were selected as resolution 500, and only 6%, around 6% of resolution frames are selected as resolution 600. In the opposite side, we have configuration C3, where all the frames are selected among full resolution and resolution 800, and because of this large frame size, it has the great performance in terms of the multi-score, but lowest FPS as processing time. So here's the comparison of DeepScale ++ and DeepScale versus other methods. As we can see, by changing configuration parameters like thresholds, different trade-off between multi and FPS can be achieved. And we can see that DeepScale ++ curve lies on the top and the right side of the figure, which means it's faster and more accurate than the other methods. And here is the effect of computation partitioning on edge devices and servers. So SOAT performs faster with comparable performance versus SO. And we can see the importance of communication between smart camera and server, like SAT performs more accurate than CO with comparable FPS. Also, here's the another slide regarding the impact of K. Where by increasing K, we have lower amount of server time, camera time, and transmission time on SOAT, and we have an opposite behavior on camera time for SAT. And here's the summary of our main contribution. We have presented DeepScale accelerating speed for more tasks by dynamically adapting sizes of input frames at runtime. We developed our DeepScale ++, and also we validated DeepScale and DeepScale ++ on variety of modes, datasets, and finally we demonstrate application of DeepScale on computation partition between edge server and smart cameras. Thank you very much for your attention.